Welcome to 17th lecture of Analog Integrated Circuits Design. We are discussing Unit 1. We started the discussion of differential amplifiers 2 days back, and we have developed the architecture, the structure of a differential amplifier with a resistive load. And in yesterday's class, we saw the large signal behavior. We saw the large signal behavior by looking at the response of uh, differential amplifier, differential output versus differential input. That is what we have seen in yesterday's class. Now, in today's class, we'll continue this and we will look at something called as common mode operation. So, for a differential amplifier, there are two things to understand. First, we have analyzed the circuit with the large signal behavior, and we realize that when your differential signal is small, there is a chance of amplification, and you will get linear amplification, and that is what we saw from yesterday's transfer characteristics of diff amp. Now, we will continue our discussion by seeing what is meant by common mode operation of a differential amplifier, and then we will come to the small signal analysis of a differential amplifier, because the whole idea of bringing this differential amplifier is to because the circuit is robust for noise, especially the noise which is appearing in common to the input terminals. That is what we are going to see. So we'll start our discussion with the same resistive load circuit, and later we will change this resistive load to transistor load for the reasons mentioned before, as resistors will be bulky, consuming more power. Yeah, so now we know that previously we kept a tail current source like this. I was telling the value of it as we call it as ISS. So this is VDD, R and R. This is M1, this is M2, and these are the outputs. So the mark here, this is Vout1 and this is Vout2. Still, I am not talking about the small signal operation. That is why I am just using the letters as capital. Now, before discussing common mode operation, what I will do is, in all practical cases, I need to replace this tail current source using an equivalent transistor. So what I will do is, just now I'll keep a transistor here, and that will be suitably biased, and I'll call this as M3. All right. Now, what I do is, so let us understand what is common mode operation. Common mode operation is when you are applying a signal which is common to both the gates of the transistor, input transistor, how the transistor will respond and what will be the output voltage. So to understand that, what I'm doing is I'm tying both these gates together, and I'm connecting that to a voltage which I'm calling as common mode voltage, VCM. Since since that voltage is connected to the input side, we are calling it as VICM. All right. So what is VICM? VICM is the common voltage given to both inputs of the circuits, both input transistors. Now you'll be wondering why I have shorted this. The idea of shorting is just to say that we are applying same voltage on both ends, right? So in order to like, instead of connecting it as two different voltages, since we apply same voltage on both gates M1 and M2, I have shorted it, and I have shown it as a single common mode voltage. In practical cases, when you apply signal, the DC which is coming along with the signal becomes common for both the inputs. So anyway, if I am shorting the gates of the two devices, and if I am connecting that to a common voltage, and if I am calling it as VICM, let us see the operation of the circuit when I have VICM. value varying from low voltage to high voltage. And also let us see the region of operation of all the devices, the M1, M2 and M3. And also we'll see the voltages Vout1 and Vout2 when you are applying a VIC. So this we'll see. So how the transistor circuit will respond to a common voltage applied to the gate of the MOSFETs. Are you guys with me? Are you following? Okay. So let us start this by considering the VICM voltage as 0. I'll keep VICM equal to 0 first. So what will happen, or what will be the condition of transistors M1 and M2 when your VICM is 0? Can I get your response in the chat box? VICM is the gate voltage connected to M1 and M2, and when VICM is 0, when your gate voltage is 0, you can say that M1 and M2 will be in cutoff region, or I'll say both are off. Cutoff means it is off only. Now what about M3? So M3, we are not connecting, we are not removing the bias of M3. So if, say for example, M3, if it is connected to VB, a bias voltage, so there is a voltage available here, and now this node, we can assume that that node voltage can be very low, because the top transistors M1 and M2 are still not on, they are off. So by just providing a gate voltage of VB, and since the drain voltage is not sufficiently high, we can consider that M3 is not in linear region, but I can say it is in deep triode region, or the starting of the linear region. I would say this is in deep triode region. So why did I say this is in deep triode region? When I say deep triode region, it can be equated to having 0 or in cutoff. But why I'm not writing it as an cutoff region is because we have provided a base gate voltage. Gate voltage exists. So what you can assume is, so if you look at the ID VDS graph, the graph is like this, and you can assume that this transistor's condition is somewhere very close to the cutoff region, because the VDS is very small. VDS could be very small, and there is a gate voltage connected. All right. So anyway, that doesn't matter for our operation, to understand the operation now. But because a gate voltage is connected, I am considering that it is in deep triode region. Now, what about output voltages? Vout1 and Vout2. M1, M2 both are off. So if these two are off, the current flowing on both the branches should be 0. So what will be Vout1 and Vout2? Can I get your response? VDD, yes. So both Vout1 and Vout2 will be at VDD. That is easy, that is simple. Now what we will do is we'll study the operation of this common mode voltage by varying this VICM from 0 to the maximum possible voltage. So now what we will do is just to look at, we know that M1, M2 both are off since your VICM is 0. Now I'll apply a voltage which is slightly more than the threshold of the MOSFETs M1 and M2. So if I provide a signal which is slightly more than threshold, I can say both M1 and M2 will start conduction because the gate voltage is slightly more than threshold. Drain voltage is already in drain voltage is in VDD. So gate is slightly more than threshold. So I can say these two will definitely starts conducting. Both will start conducting because the current will flow. All right, so the current will flow for sure. Now, if your VDS is greater than VGS minus VT, I can say that it will be in saturation. But just at the when you provide a voltage slightly more than VT, it is just the onset of saturation, I can say. But M3 would have come little more higher. M3 would have come little more on the top side, so it would have come to triode region. And what will happen to your VDD voltage, output voltage? VDD will start reducing. So I can say, I'll write here, the previously it was VDD. As the current started because both M1 and M2 started conducting, VDD will start reducing. All right. Now, so we are looking for a condition when all the three transistors are in saturation. All the three transistors should be in saturation because we wanted an amplifier. So transistor should operate as a ideal current source or at least a practical current source. Now the question is, uh, in order to keep all the three transistors in saturation, what should be the minimum common mode input voltage? Uh, are you getting my question? So VICM started with 0, it has come to VT. So at VT or just on the VT, it will start conducting, and slightly if you increase, it will start, the current will start flowing and your output will reduce. But still we cannot assure that the transistors will be in saturation. In order to assure the transistors to be in saturation, what condition I should say, or what should be the minimum common mode input voltage? Any idea? Can I get some response in the chat box? All right, so for the transistor to be in saturation, so for M3 to be in saturation, the drain voltage should be minimum. This drain VDS should be minimum some voltage, and we generally call that as overdrive voltage or VDS sat of the device, so VOV3. And along with that VOV3, I should also have appropriate VGS here so that a current will flow. So the minimum input common mode voltage here, what we can call it as VICM minimum, can be written as VGS1 plus VOV of 3. So what is the meaning of this? When I provide a DC voltage, when I provide a voltage which is equal to VOV3 plus VGS1, VOV3 plus VGS1, and if I am giving that voltage to the gates of both the transistors, I can ensure the saturation region operation for all the three transistors. VGS1 or 2 minus VDS3. That is, yeah, Avinash and Akash, I think you have written answers. But I'm asking for VICM minimum. Yes, it should be plus. So in this case, I can say that all the three transistors will be definitely in saturation. And if all are in saturation, and since the voltage on both sides are equal, equal currents, say if this the current flowing through this device, if it is ISS, the current flowing here will be ISS by 2, and this also will be ISS by 2, and I can say output is equal to VDD minus ISS by 2 into R. It could be R or RD. So anyway, it is drain resistance. So this is a minimum voltage. So as we mentioned about a minimum voltage, do you think there is a maximum voltage also which will ensure the saturation condition of all the three transistors? VICM maximum? Or will I'll ask the question in this way. Can I have any voltage? Can I connect any voltage here to this point? Can I keep on increasing this VICM such that I can always say the transistors will be in saturation? No. So what is the condition, or what can be the, so the gate voltage can go up to which voltage? What voltage? All right, look at this. Now, if you look at this point, what is the drain voltage now? Drain voltage is this VDD minus ISS by 2 into R. So if I look at any MOSFET, in order to retain the saturation condition, we know that drain and gate can have equal voltages. Drain and gate, if both have equal voltage, then also the device, I can say it will be in saturation, right? Because always the condition is VD should be greater than VG minus VT. All right, so if both are at equal voltage also will ensure saturation condition, or your gate can actually go one threshold. Gate voltage can go actually one threshold higher than drain. I'll mark this side. the gate voltage can go one threshold higher than drain. That will also ensure the saturation. That is directly from this relation, right? So Vd greater than or equal to Vg minus Vt is the condition. So your gate voltage can go maximum what? Your Vg should be less than Vd plus Vt, less than or equal to Vd plus Vt. So gate can go maximum one threshold higher than a drain in order to ensure. So this also will ensure saturation condition. If that is the case, how will I write VICM maximum? Now the drain voltage is VDD minus ISS by 2 into R, and this gate voltage can go one threshold higher than this. So by applying that principle, I can write that VDD minus ISS by 2 into R is a present drain voltage. Gate can go one threshold higher than this also. Even for this condition, both transistors will be in saturation. Yeah. So at that time, I cannot write that V out 1 and yeah. So your V out 1 and V out 2 will be still if it is flowing, the equal currents are flowing, and that will be equal to the same VDD minus ISS by 2 into R. All right. So what we have analyzed just now is for a differential amplifier, whenever we connect a signal to both the terminals for on both the gate terminals, there will be some common voltage there. So I'll give you a little more clarity how this common voltage is coming. So and that common voltage should be within some range. What should be that range? This is the range. Why that common mode voltage should be within this range? If it within this range only, all the three transistors will operate in saturation region, and this particular range is called as input common mode range, or ICMR, input common mode range. And the minimum value of input common mode range is this can be less than or equal to VGS1 plus VOV3, and maximum is equal to VDD minus ISS by 2 into R plus VT. So this is the range of input common mode voltage. We call this as input common mode range. Any doubts on this? Any questions? Any questions? Is this clear? All right. So what if ICMR exceeds the maximum value? Yeah, tell me what will happen if ICMR exceeds the maximum value. Uh, ICMR is a range, right? So if you try to give a voltage to the gate which is more than this, tell me what will happen. Just now I told, right? So gate can go one threshold higher than gate. Sorry, yeah, gate can go one threshold higher than drain. If it is going more than that, what will happen? Any guess? So this is a condition for saturation, right? Vd should be greater than Vg minus Vt, greater than or equal to. From this I can say Vg should be less than or equal to Vd plus Vt. So if Vg should be always less than or equal to Vd plus Vt. What will happen if it is going more than that? Yes, both transistors M1 and M2 may leave saturation region and it will go to linear region or triode region. Yeah. So that is why we have to maintain transistors in saturation region by providing suitable voltage to the gate. Is that clear, Ayushi? Thank you, Bhuvan, for the response. Yes. So now, so this is common mode operation. Now I'll tell you one simple. Okay, so let us discuss small signal analysis too, and then we'll come back. So now we will see small signal analysis of differential amplifier. So as our circuits will become bigger and bigger, small signal analysis will become easier and easier. It will become more easy to do small signal analysis of differential amplifier or even a larger circuit than single stage amplifiers. That you will get to know when I do the small signal analysis of this. All right. So now I'll go back and take the first circuit what we have discussed. Meanwhile, if you have any questions from common mode operation, you can think, and if you have questions now, you can ask also. So as we are studying, doing common mode and small signal analysis, I'm just keeping the tail current as current source itself to make our analysis easy, and later we will replace that. All right. Now, so this is a circuit and this is the point. So now I'll use all small letters. This will be Vout1, this will be Vout2, and I'll be taking output between this as Vout or either. So what is the output here? It will be Vout1 minus Vout2 will be the Vout value. All right. Now to the gate, I will apply a signal. And to this gate also I should apply a signal. So from the previous discussion, you know that when you apply signal differentially, I'm just marking like this to say that or to show that you are applying a signal which is differential. All right. Now yes, Bhuvan. So yeah, that's a good question. So VICM in most of the cases, whenever we design a circuit, in most of the cases that will appear as a DC voltage, right? But you see, this is the point, or this is what we told, that differential amplifiers are immune to noise, or it is robust for noise. Why? Because see, generally noise will affect all points in a circuit equally. Noise will be that is in general with noise will affect all the points of a circuit equally. So in that case, if noise is affecting this point and this point, if it is equally, if it is affecting, will it affect the performance of a differential amplifier? Just I'm asking a question. Can you guys think and tell me? Now if you look at the output here, Vout1 and Vout2, whatever common signal we are connecting, Vout1 and Vout2 both are responding same. The response remains same. Now, if the response is remaining same, when you measure the voltage as differential voltage, that is plus we are measuring at measuring at this point with respect to the other point, since both nodes are responding equally to the signals, the difference voltage will be always zero. Yeah, that will get cancelled out. So that is the beauty of the circuit. When you provide equal signals to both the gates, the circuit will produce equal outputs at both the signals. And when you measure the voltage differentially, you will get those signals get cancelled out. So that is the beauty of the circuit. That is how we say that the circuit is immune to noise. Thank you for asking that, Bhuvan. Maybe others also would have got clarity. Yeah, so in general, if a signal is coming there like a noise signal, definitely it will respond equally, and that will get cancelled out. Now regarding DC, yes, there is a DC. We are generally talking about the DC because that is what is setting the DC operating point, and generally that DC voltage should be common for both the sides. Is that convincing, Bhuvan? All right, yeah. If you have further questions, I'll definitely take. Now, now look at the circuit here. What I have done is I have connected two separate sources. One to the input of transistor M1, and another one to the input of transistor M2. This is M1 and this is M2. This is VDD and this is R. So, what is the meaning of this connecting in this way? It is same as this, right? Because both gates are same, so it is same as this. Or even I can say, see, when if I want to apply differential signal, how should I apply? I should actually apply differential signal like this. A signal should be applied like this, isn't it? To a differential amplifier, I should be able to even apply differential signal. Generally, when in the case of op amps, we will actually connect one and keep the other potential as ground. But if you really want to apply a differential signal, that should be in this form. So what I'll do is I'll mark this as differential voltage Vd, and since it is at the input side, I'll mark this as Vid. All right, Vid is the differential input voltage. Now this Vid I am just breaking, and I am writing it as Vid by 2 on this side. This is for our understanding purpose I am writing, minus Vid by 2 on the other side. So what is the differential voltage in total? It is Vid. So plus minus, this is minus Vid. So what is the voltage in total? It is Vid, right? Vid by 2 minus Vid by 2. So in total it is Vid voltage is coming across the two gates. Is this clear till this point? Is this clear or you have doubts? Actually, we have to connect a differential voltage, but for our understanding purpose, I am just breaking that Vid into two Vids. One, I'm breaking that into one Vid by 2 and one minus Vid by 2. Is that clear? Can I get your response, please? Yes, Avinash. So what I was telling is, you want to apply differential signal. That is what you can see now. That is Vid. All right. Now, if I want to the same thing, I am just drawing in a different way, or I'm just connecting in a different way by keeping one signal here, grounding it, in this form, and I'm writing this as Vid by 2 and this as minus Vid by 2. So what is the differential voltage available here? Vid by 2 minus Vid by 2, which is equal to Vid, right? So then I am just deleting this. How am I deleting? I am telling that the differential voltage still is Vid. Is that clear, Avinash? Yes. What about others? Is that clear, or still you have doubt in that? All right. So if you have doubt, please ask me. I'll repeat and I'll give clarity on that. Now, further, what I'm doing is, we cannot just like that apply a signal to the gate. There should be a sufficient DC voltage, and that DC voltage I'm marking here as VICM. So both the transistors we have applied a DC signal, and on that DC you have this AC, and on one side it is like this Vid by 2, on the other side it is like this, which is minus Vid by 2, and if you measure it as differential, you will get Vid in total. I hope this is clear, this picture. Now we can actually understand the small signal. So all this explanation and this build up is just to tell you about the small signal equivalent circuit analysis. That is, see, the thing is very simple. So we can study the differential amplifier under two headings. So the first heading, what I will do is, I will the first heading is, if the circuit is symmetric and the inputs are anti-symmetric, we generally analyze in the way which I am going to tell you now. So that is generally called as, let me mark it as case 1, where you have a symmetric circuit with anti-symmetric excitation. All right, there is a question. Is a DC voltage applied to keep the M1 and M2 in saturation? Yes, that is what we told, right? When you apply VICM should be in the range of VICM minimum to VICM maximum. Is that clear, Akash? All right. Yeah. So what I'm going to teach now, listen very carefully. If you understand this, you can solve the differential amplifier circuits in less than 1 minute. That is a technique what we'll be learning, we'll be trying to understand now. All right. So the what I'm going to consider now is a symmetric circuit. If you have a symmetric circuit and the excitation is anti-symmetric, how will you analyze the circuit? So look at the circuit, whether the circuit is symmetric. Quickly answer my questions also in the chat box. Whether the circuit is symmetric, the circuit, whether it is symmetric or not. Yes, it is symmetric. So if any circuit of anything, if it is symmetric, we generally mark something called as a line of symmetry, and this is the line of symmetry. So the circuit is symmetric, and this is line of symmetry. Whether the excitation, what is meant by excitation? Excitation is nothing but input. Whether the excitation is anti-symmetric, again I'm asking question, you can quickly respond. Whether the excitation is anti-symmetric? Yes, excitation is anti-symmetric because on one side it is VID by 2, on other side it is minus VID by 2. All right. Now listen carefully. You have a circuit. We know that, or from the transfer characteristics also, we understood that even for this differential amplifier, there is a linear segment in the transfer characteristics, and we want to design a linear amplifier out of this. All right. So what is the meaning of that? The circuit in total is linear. I'm not talking about the operating region of the transistor. I'm talking in general about the circuit. We are looking for a linear circuit. All right. So what I will do is I will just represent the entire circuit in form of two blocks. I'm going to represent the entire circuit in form of two blocks. One block is like this on this side, and another block is on the other side. So what I am assuming is inside there are all the elements of the circuit. So I'm just representing the circuit here in form of a block, and on this side I'm connecting the signal VID by 2, and this side I'm connecting the signal minus VID by 2, and there will be a lot of connections in between, and if you look at the main circuit, even in the line of symmetry, there are some in the line of symmetry there is something connected. So this is the line of symmetry. I'm actually connecting some devices over there, right? Do you understand what I have done here? I have assumed that the circuit is symmetric and circuit in total is linear. So whatever I am assuming inside this will be having different nodes, say up to 1 to n. This also will have n nodes inside. The circuit is symmetric, or both the blocks are linear and symmetric. Is this clear? Can I get some quick response? Yes or no? Can I get some response quickly? All right. Okay. Now look at this. So what I will do now is, say I'm going to apply VID by 2 on one side and 0 on the other side. So if you look at this block, which is written in pink, there are two input signals coming in. One is VID by 2 and another is minus VID by 2. So what I will do first is I will apply only one signal here, and I will short the other signal to ground. That is what I marked here. VID by 2 on one side and other side I am giving 0. And when I measure the voltages here at these lines, in these points, I got, say I measured it as Vx here, Vy here, and Vz here. All right. So let me do one thing. Just hold on. First, I am providing VID by 2 on this side and 0 on the other side. And when I have given VID by 2, I just measured the voltages coming at these points, and I measured it as Vx, Vy, and Vz. Is that okay? Just I measured. I do not know exactly what is the voltage, but definitely voltage will be there, and I just marked it as Vx, Vy, and Vz. Now what I'll do is I'll keep this as 0, this side as 0, and I'll apply VID by 2 on the other side. All right. So if I do this, what can be the expected voltage at these 3 points? Is it same or different? Again, a question I'm asking, yeah, same as before. So I should get it as Vx, Vy and Vz. What is the reason for that? I have assumed that the entire system is linear and the system is symmetric also. So if I am providing one same voltage, it should actually respond in a similar way. So I will get Vx, Vy and Vz. But actually what I have given, I have not given Vid by 2, I have given minus Vid by 2. So what I will do, I will just change it. I will change that to 0 and minus Vid by 2. Now what will be the difference now than before? When I have given Vid by 2, I got Vx, Vy, Vz. Now if I am giving minus Vid by 2, what should be the response? Same or, yeah, it will be minus. So I can say that now I will get negative values of the previously measured voltages. Yes, very good. Now, but I am not working with the circuit with separate voltages. I applied superposition theorem now. Now, if I combine these two voltages together, that is, if I provide Vid by 2 here and minus Vid by 2 together, can you tell me what will be the voltage in the line of symmetry? What voltage will be there in the line of symmetry? What will be the voltage in the line of symmetry? When you have Vi, yeah, it should be 0, right? Because one side it is Vx, other side it is minus Vx. So what I can expect is, here I can say this voltage can be 0, this can be 0, this also can be 0. Alright, so why it is 0? Because you got opposite magnitudes, right? Vx one side and minus Vx one side. So the sum there will be equal to 0. So what is the takeaway from here? When you have a symmetric circuit and when you are providing anti-symmetric excitation, the line of symmetry potential is at 0 volt. The line of symmetry potential will be at 0 volt. Now how will it help us in understanding or in further analysis? So now look at the circuit diagram here. This is a symmetric circuit. The excitation is anti-symmetric. So the line of symmetry point is this. Now this will be equal to 0, or this can be considered as ground. Right. If that is ground, how it will help our analysis? If that point is ground, the analysis or the circuit is as same as a simple common source amplifier, isn't it? So since the line of symmetry point is at 0, no need to analyze the entire circuit. If we analyze only one half of the circuit, that itself is sufficient. Are you guys with me? I am asking again and again just to know that you guys are following me or not. Since the line of symmetry point is at 0, we no need to analyze both the sides. Yeah, only one half part if you analyze, that is enough. Why that is enough? Because both are same. The middle point is connected to 0. Are you guys with me? Alright, so the takeaway here is, if whenever you have a symmetric circuit with anti-symmetric excitation, line of symmetry points will be at 0. In that case, you can analyze the differential half circuit. We call this as half circuit analysis. So what is the differential half circuit of the previous diagram? So the previous circuit was like this. So I will draw only the half circuit here. This point is ground. Now what is input here? Input is Vid by 2. Output I marked as V out. Actually it is V out 1, or I can say that it is V out by 2. Because it is half, the other half is on the other side. Alright, now how will I analyze this? So I will analyze this in this way. I know that V out 1 is equal to the output is equal to minus GMR into VID by 2. But V out 1 is V out by 2. So what is that I want to find? I want to find what is the differential gain of the circuit. What is differential gain? Differential gain is equal to V out by V in. Differential gain is equal to V out, the output differential voltage, divided by the input differential voltage. Now I have V out by 2 is equal to minus GMR into VID by 2. 2 and 2 will get cancelled, and I will get V out by VID as equal to minus GM into R. All right. Now tell me whether you need to analyze the entire circuit. No need, because if you analyze only the half circuit itself is giving you the differential gain value, which is equal to minus GM into R. Is this concept clear? I want to, sir, what does 3 line in those block represent? What is that? Okay, here, this pink color. So what I was trying to say is, see, I want to, there can be multiple connections, right? So in this specific differential amplifier example, you have only one point. So you can think of only single line over there. Even in that case, it will be zero. The middle point will be equal to zero. So what I meant by that is there can be connections from both the sides, and even in those connections there can be some devices connected. Is it clear, Avinash? All right. So quickly I will give you one question. Tell me how you will solve this. All right. So this is M1, M2, M3, M4, and M5, and this is VDD. Now, yeah, Akash, your question is, so M3 will be in off state. Which M3 will be in off state? Okay, are you, I didn't get that. Are you asking if the current source is replaced by a transistor and that will be off condition? Is that, Akash, you're asking? No, Akash. No, it will not be. So, when can you say that a transistor is off or on, depending on the DC voltage which you're applying to that, right? So DC voltages will be always there, and that will keep the devices in saturation. Now, for small signal analysis, since there are no changes for the DC, we are assuming that those are at zero. The meaning is there is the change is zero. All right, is it clear? So this is to everyone I am telling. So whenever we whenever we analyze small signal, we always say that DC voltages will be equal to zero. The meaning is the change in those voltages are zero. That is why we are marking it as zero, because small signal analysis or small signal circuit represents always devices or elements which is having incremental changes. All right. Okay. Yeah. So come to this question, and can you guys quickly solve this? The only thing, the question is compute the voltage gain. Compute voltage gain if input voltages are anti-symmetric. In certain cases, they will not mention it is anti-symmetric or not. If it is not mentioned, you can assume that the excitation is anti-symmetric, and you can proceed with the calculation. Also, one more thing is given: lambda is not equal to 0. Yes, Akash. DC voltage will be there. DC voltage is without making transistor, without providing proper DC, transistors will not enter into any of the operating regions. So in all the discussions, it is understood that, or it is default that DC is there. All right, Akash. Yeah. So I think the question is here, and can you guys let me know the answer for this? Very good, Ashita. I think you got the answer. Minus GM1 into R01 parallel to 1 by GN3 parallel to R03. Very good. So how will you solve that? Yashita, can you unmute and tell me how did you solve it?
The M3 is diode connected load,
Yes.
so gain is GMR, so R out will be R01 parallel with 1 by GMR3 parallel with R03.
Very good. Yeah, that is right. So when you analyze the circuit, thank you, Yashita, for that. So when you analyze this, since it is given that input voltages are anti-symmetric, what you should do is you can just mark a line here. This is the line of symmetry. Since the input signals are anti-symmetric, this node will actually go to ground. So then what you should do, you should draw the half circuit. So what is the half circuit here? The half circuit is this. I'm telling this should be the way when you analyze it on an exam, or like when you write it, it should be in this form. And you can mark this point to ground because this is a common point which is connected to 0. Now what is here? How will you modify this? The input here is VID by 2 because it is given that input voltage is anti-symmetric. VID by 2. So this is M1, this is M3, and the output here is V out by 2. It is V out 1. V out 1 is actually V out by 2 because we measure it as V out differentially like this. So you are asked to find the voltage gain. So now how will you write that? This is a simple common source amplifier only. So AV can be written as minus GM1 into the output resistance. Output resistance is resistance looking up here, which is R03 parallel to 1 by GM3 parallel to the resistance looking down as R01. So this will be the voltage gain. Right. That's it. So it is very easy to yeah. So can you tell me now? See, compared to the single stage amplifiers, now you have 5 transistors in the circuit. But how easy is to find the small signal gain compared to those circuits? That is what I told. As we progress now in the next unit, we will see operation amplifier circuit. There, the analysis become much more simpler, or it will be almost same like this. So, any questions now on this small signal analysis? Yes, there is a question. The circuit will only be symmetric if M4, M3 are identical. Yes, yes, that is also there. M3, M4, M1, M2, all those. That is what now. This, yeah, you can say that the circuit is symmetric in that case. Yeah, that is right. That is a right observation, Bhuvan. Avinash, I didn't get that. Minus 2 GM1 into. Okay, Avinash, can you unmute and tell me why you have written that minus 2 there?
So, because we have considering two such identical common source.
Yes, two common sources are there.
So, sir, when we shouldn't we add up the gains there?
How you are adding up the gain? So that is what I have written here. No, then actually I should find what is V out by 2. So if you write V out 1 will be with respect to. So your V out by 2 is equal to V out 1. Are you getting this? Definitely when you measure, your signal voltage will be the output swing will be double. That is for sure. Output swing will be double, but your gain remains as minus gm, sorry, minus gm1 is this, minus gm1, because what is your v out 1 in this case? V out 1 is equal to uh, yeah, minus gm1. If I write like this, minus gm1 by 2 into r03 parallel 1 by gm3 parallel r03. Is this clear? So what I am writing it as Vout1 is voltage from here with respect to ground. Vout2 is also from this point with respect to ground. But we are not measuring like that. We are measuring from Vout1 with respect to Vout2. So Vout1 and Vout2 are actually half of Vout. Avinash? All right. Okay, Avinash. Yeah. So fine. So we'll wind up today with this, and we will continue in the next class. Please wait. So if you have questions, you can ask. And thank you so much for joining for today's class.